Hi, everybody. Welcome to Chapter 9, Part 1. Chapter 9 is about multivariate correlation. So Chapter 8 was about bivariate correlation. Remember, bi, 1, 2, two variables. So multivariate, we're going to include more variables in this whole thing. So to start with, let's do some review. I want to cover one other concept, and then we'll start talking about Chapter 9 stuff in earnest. So here's the first question. I think that eating vegetables makes you smarter. I asked participants to indicate whether they had eaten vegetables, yes or no, and then I measured their GPA. How many variables do I have here, and what kind are they? Okay, in this case, I have one categorical variable and one continuous variable. The categorical variable is whether you ate vegetables, yes or no. Those are the two categories. And the outcome, GPA, is a continuous variable, right? Because higher GPA means more better grades, at least, right? So this is one categorical and one continuous. Now, before we go any further, though, that's just review. We need to talk a little bit about something called the criteria for causality. Now, in the book, you've seen this already a few times, okay? The criteria for causality comes up several different times in the book in a variety of ways. And what it's saying is, even though correlation doesn't equal causation, in order for us to show actual causation, we need to be able to establish these three things. And experiments can do this. Other things can't fully do this, but they can give part of it. Even a correlational design can give us part of the criteria for causality. And covariance is one of those parts. So covariance just means as one thing goes up, the other thing goes up, right? That's all that means. So let's say that, let's talk about this in a bivariate way, and then we'll add some more variables and talk about what that means. So let's say that I have a hypothesis, okay, that attending my lectures attendance is associated with, or influences at least, grades in my class. So let's say that attendance in my lecture is associated with your grade in the class, okay? In a bivariate way, what we're looking for is, does attendance and grades, do they covary? What that means is, as attendance changes, do grades change? So that's what we're normally thinking about when we think about a correlation. Attendance and grades kind of affect each other somehow, right? That as attendance moves, grades moves, okay? Now, why? Why does that happen? Well, sometimes you can figure out temporal precedence. Temporal precedence just means in time, can you figure out which one is affecting which? So in this particular case, attendance and grades, let's say that the grade that I care about is an exam grade. And so I can establish temporal precedence. I can say, hey, people who attended before the exam, right, because attendance came first, had better grades, okay? I can do that sometimes with correlation. Okay, sometimes we can do that. And if something causes something else, then the thing that caused it, the independent variable, has to come before the dependent variable. Fine. Many times I can't do that. And a lot of the correlational designs that we do, you can't do that. So for example, in your first project, if you're talking about like intentions to exercise and attitudes towards exercise, you can't tell which one's coming first, right? Because you're measuring both at the same time. Internal validity is how much can we be sure that the thing that came first, right, which we hope is the independent variable, how much can we be sure that it was actually attendance? Let me see if I can get this to work again. That it's actually attendance that causes the change in the grades and not something else. So let's go back. Sorry, trying to get my pen to work. Okay, how can we be sure that it's actually attendance and not something else that's causing the change in the grades? Well, why is this such a big deal? Well, this is such a big deal because we need to know, let's see, we need to know if there are other variables out there. So let's put another variable in here. Let's say that other variable is work. And I'm not talking about how hard you work in the class. I'm talking about employment. Okay. What if it is that we found this relationship that grades and attendance covary, right? That they affect each other. As attendance goes up, grades goes up. And we know that attendance came before the exam grade, so that's temporal precedence. The internal validity is, how do we know that it's attendance and not something else that's causing the change? For example, could it be that work, right, is causing the change in attendance? That is, if you're employed, you're less likely to attend my class, my lecture. Could it also be that work causes a change in grades? That is, that as you work more, your grades go down because you have less time to study. That means that the correlation, right, the relationship, let me just go and kind of show you this. The relationship between attendance and grades right here is actually caused by a third variable called work. This is called a third variable problem. A correlation, it's hard to establish that internal validity because something like your attendance could have been caused by how much you work. And work can also be the thing that's causing the change in grades. It may be that attendance and grades actually have no relationship whatsoever. So let me erase those. It could be that by themselves, attendance doesn't cause a change in grades. Work is causing a change in both. That's called a third variable problem. And it's a problem for the internal validity of the idea that attendance is changing the grades. When you run an experiment correctly, then you can randomly assign people to either attend or not attend lecture. And that way, any other variable, like whether they work or something else, is not the one that's affecting it. Okay, now, in this particular chapter, we want to talk about more than one variable. We're not going to talk about the third variable here as necessarily a third variable problem. We're going to try and figure out some of the internal validity and the temporal precedence, all this criteria for causality, without actually running an experiment. All right? So what we're trying to do is, instead of worrying about this third variable problem like we have here, which is a problem for internal validity, we're going to add a new variable and try and find a way to help ideas of internal validity, even though we have a correlational study. So let's keep going with this. I'll show you basically what we're going to talk about. We're going to talk about the different designs that we have that we can do in psychology. And specifically, we're talking about designs that can happen in any kind of a study. But generally, we're talking about, when we're talking about this, we're talking about correlational designs. We're also going to talk about multiple regression. This is the big thing that we need to discuss. Multiple regression is the big thing we need to discuss, what it is and how it works. And then we'll get into mediation and moderation probably in the second half of this chapter. So let's go ahead and start by talking about designs. Okay, let's talk about different kinds of designs. Let's start with cross-sectional versus longitudinal. So this is for any kind of design. It doesn't really matter if it's going to be a correlational or if it's going to be an experiment. You can do them with either. But today we're talking specifically about correlational studies. Cross-sectional just means it happens at the same time. The cross-section means a cross-section of time, right? We've got this population. We take the sample, and it's a cross-section in one time. So, for example, if I wanted to know whether or not studying causes a change in your grades, then the cross section would be I measure studying and grades at the same time. Okay, I'm not looking over a long period of time. I'm saying today you took this exam. How much have you studied? And that's it. That's the cross section. Longitudinal looks at this over a longer period of time. So I wouldn't just look at your studying at one period of time. I would look at your studying across a long period of time. And I wouldn't look at your grades at one period of time. I'd look at it at a variety of times. So in longitudinal studies, you have a long period of time in multiple time frames where you've measured the variables that you're worried about. So specifically, when we're talking about ideas of autocorrelation means that the correlations are inside of the variables that inside the same variable, right? Or inside the same time. So for example, if I want to see how studying affects your grades in a longitudinal study, I might look at how much you studied in your freshman year, your sophomore year, your junior year, your senior year. So those are 3 different times, and I'm measuring how much you studied and your grades in each one of those. Okay? Autocorrelation would look at the correlation between study and grades within the year sophomore, for example, right? That would be the autocorrelation because it's in the same time. Or you might be looking at the correlation of all of the exam grades, right? So all the grades are correlated with each other. And then separately, all of the studying is correlated with each other. Cross-lag is crossing over time and variable, meaning I would look at study time when I'm a sophomore compared to grades when I'm a junior. Grades when I'm a junior compared to study time grades when I'm a junior compared to study times when I'm a sophomore, right? That's what we just really did. And then grades when I'm a sophomore compared to study time when I'm a junior. Now, the reason why you might do a cross-lag study would be to establish that that those are not correlated the opposite way temporally, meaning in time. So if my grades, my studying when I'm a sophomore can predict my grades when I'm a junior, then studying should be predicting grades. However, if I look at my grades when I'm a sophomore compared to my studying when I'm a junior, if those don't correlate, then that's a good thing for me, right? Because I'm saying that studying causes the change in the grade, right? So if I look at the cross-lag, it can establish the temporal precedence, even though it's a correlational study. All right. When we've been talking about bivariate correlation, we talked about Pearson's R and a t-test. So Pearson's R, you got 2 continuous variables. A t-test, you have 1 categorical with 2 levels and then 1 continuous variable. Okay? Those are bivariate because you're talking about 2 variables. Now we need to move on from this and start talking about multivariate correlation. And specifically, we're going to be talking about multiple regression. Multiple regression. Now, multiple regression is when you have more than one predictor variable, and one outcome variable. So let me say this again. In multiple regression, you have more than one predictor variable. Now, in this class, all of the variables that we're going to talk about in multiple regression, they're all going to be continuous. Okay? In reality, you can use categorical variables, but for us, we're only going to use continuous to keep it simple. The outcome variable has to be continuous. Now, the difference between a bivariate correlation like a Pearson's R and a multiple regression is that we're going to have multiple variables predicting one other variable. When we were talking about a Pearson's R before, it didn't matter, which one was supposed to be causing which, because, it's just a correlation. That doesn't really matter. But in this one, we really need to know what is the outcome variable, like the dependent variable, and what's the predictor variables. Those are like an independent variable, but they're not being manipulated because this is correlational study. So let me give you an example. We're going to do an example. Oh, first I need to give you these terms. In multiple regression, we need to talk about capital R versus lowercase r. A Pearson's R is a lowercase r. That's the statistic you're supposed to use. Multiple regression uses both a capital R and a beta. So this capital R, when you run a multiple regression, which is a specific statistic that you're going to run, you're going to get a capital R and you're going to get a beta. And we're going to discuss what the differences are, but let me just tell you definitionally what they are. Capital R is the effect of all of the predictor variables on the outcome variable. All the predictor variables on the outcome variable. Beta is the effect of one predictor variable on the outcome variable, independent of any other predictor variables, without the influence of any other predictor variables, controlling for the influence of any other predictor variables. So, to understand what this means, we're going to go through an example, but I want to make sure that we're totally clear. Multiple regression is when you have more than one predictor variable and one outcome variable. The way we're going to do it in our class, all of those variables are going to be continuous. Capital R is all of the predictors variables together, all of them together on the outcome variable. Beta is each individual predictor variable's effect on the outcome variable without the influence of any other variable, without any overlap, without any other influence at all. Let me show you what I mean. All right, so let's take a look at this. We have an outcome variable. This is going to be our outcome variable is happiness. Let's say we have a happiness scale, for example. Okay? When we're doing bivariate correlations, we're looking at one variable against happiness. So for example, time with friends, how much time you spend with your friends. So let's say that this right here, R equals 0.81, is the bivariate correlation, the Pearson's R, of time with friends and happiness. It's how much they affect each other. Okay, does that make sense? That's just the bivariate correlation. We can run a separate bivariate correlation of relationship satisfaction, right, on happiness. So R equals 0.61, that would be the correlation of relationship satisfaction on happiness. Now what this looks like then, let's go ahead and try and use a pen on this. See if this is going to work. Nope, not going to work. So what this looks like is we've got the influence of two variables with each other. So these are bivariate correlations, right? So this is happiness, and this is time with friends, right? And these are correlated with each other. Okay, that's what R equals 0.81 is telling you. Conversely, we have a separate analysis that says we have happiness and we've got relationship satisfaction, and those are correlated with each other. All right? Okay, but I have a question for you. Could it be that relationship satisfaction and your time with your friends are correlated with each other? Could it be that they overlap with each other a little bit, right? Could it be that these things all have effects on each other? Another way to look at this, and so don't worry about this with ideas of circles and squares. Another way to look at this is with a Venn diagram, all right? Is with a Venn diagram. In the Venn diagram, we're going to have the three different variables. So let's look at happiness. So happiness is going to be right here, okay? All right? And then we're going to have the other two variables. So we're using a Venn diagram now. It's going to be a little bit different. So this is going to be time with friends. And then this is going to be relationship satisfaction. Okay? Now, if you think about it, relationship satisfaction and time with friends, those should actually influence each other. In fact, they might overlap quite a bit. And what we're interested here in is saying, hey, what is the effect of relationship satisfaction and time with friends on happiness? Well, a bivariate correlation can't do that. This relationship satisfaction, R equals 0.61, what it's looking at in the Venn diagram is just, let me get a different color here, is just the yellow part. It's the overlap of relationship satisfaction on happiness, right? It doesn't know that it's overlapping here with time with friends. It doesn't know. It doesn't have any idea, okay? Conversely, time with friends, that Pearson's R right there, is only telling us this amount, right? It's telling us time with friends on happiness separately from the influence of relationship satisfaction. Now, wouldn't it be cool if we could figure out, since we think that relationship satisfaction and time with friends, overlap with each other, wouldn't it be cool that if we could figure out how much it is that spending time with your friends affects your happiness independent of how satisfied you are with a relationship, right? Without the influence of the other one, okay? Wouldn't it be cool if we could go in there and figure out what is the effect of just time with friends without any of that stuff over there. And I know that doesn't look right because I erased it the wrong way, but that's where we're getting at. Let me show you the example. Let me show the example. All right, in a multiple regression, what we are going to do is first we are going to get time and satisfaction together. So time and relationship satisfaction, both of them together, their influence on happiness, that's going to be capital R. So let's do these again. So here, I'll put it over here this time. So here is happiness. Okay. All right. Here is relationship satisfaction. Relationship satisfaction is the red part. And here is time with friends. All right, now, capital R, that 0.7 right over there, that is looking at the combined influence of both relationship satisfaction and time with friends on your happiness. Okay? How much both of them together affect it, right? So specifically, it would be looking at all of this, right? The combined effect, both of them together, right? That's what it would be looking at. The beta looks at the influence of, let's look at time alone, for example. The beta equals 0.58. That is the influence of time without any influence of relationship satisfaction here. Okay? So let's get rid of those yellows, and I'll show you what beta looks like. Beta, let's see if I can get the yellows. Oh, lost it. Put that T back. All right, so the beta looks only, let me get a different color on this one as well. Let's get back to that orange. The beta of time alone is only this. Okay? And it stops there. It's only the influence of time on happiness without any of the influence of relationship satisfaction. Notice how it doesn't include this section over here. Okay? The beta looks at the influence of time on your happiness by itself, just that orange section right here, just this part. It does not include any aspect of relationship satisfaction. Statistically, that's being taken out, it's being removed. Conversely, the beta weight for satisfaction alone, that 0.11, is this, just the influence right here with no overlap. And what this is saying, if you look at it, and hopefully you can see it, maybe I'll kind of try and move over so you can see all of it, right? Because I know that sometimes you can't. Okay? You see that? Beta equals 0.11. P is greater than 0.05. What that's saying is that even though the bivariate correlation was significant, when we statistically take out the influence of relationship satisfaction, time alone has a significant influence on your happiness. But relationship satisfaction does not. Relationship satisfaction does not. The difference between, see that yellow part that I've put in right here, and it's not being overlapped right there, okay? We've taken that part out. Statistically, we take that part out. And when we do, we find that relationship satisfaction really doesn't have a significant effect. That's what a multiple regression does. It can statistically control for, it can statistically remove the effect of one of the predictor variables on the outcome variable to look at the effect of time alone, or whatever the predictor variable happens to be, on the outcome variable. All right. We will do more of this in the second half. Let's do a review question. I think that eating vegetables makes you smarter. I asked participants to indicate whether they had eaten vegetables, yes or no, and then measured their GPA. What statistic am I going to use? This is a bivariate. This is bivariate, okay? Bivariate correlation. And one of those variables is categorical with 2 levels. So eating vegetables, yes or no, that's 2 levels, right? And the other one is continuous. That means you use a t-test for that. Okay, let's go ahead and stop there.